Okay, so today we're going to be talking about properties of waves. Okay, so we talked about yesterday that a wave is going to be a sinusoidal wave or a simple harmonic wave. So if we take our pendulum that's going back and forth like this and we were to plot it on a graph, we would end up having what's called a sine wave. And most of you have studied this already in your pre-calculus class. So properties of a wave. First off, a wave is a disturbance of energy. So it's going to be energy that's going to be pushed down for something, down a pathway. So if I took some energy in a pendulum, what's going to happen is this is going to be the energy, and the energy is going to be pushed down. So we're going to have energy that's going to be increasing and decreasing, and this is what causes what we call a disturbance. Okay, so this is going to be energy that's going to be pushed down a pathway. Okay, another property of a wave is the wave has to go through a medium. And we call a medium is just an environment that a wave can travel through. So a medium can be water, it can be air, so it's going to be some sort of fluid. So if it's in a vacuum, there's no medium, there's nothing in there, therefore it doesn't have, it's not a property of a wave. Now there's type of wave that we're going to be dealing with, which is called a mechanical wave. These mechanical waves have to require a medium. So the waves that we're going to be talking about in this class all have a medium that they're traveling through. There's two types of mechanical waves that I'm going to go into in the next slide. We have longitudinal and latitude waves, or what we call transverse waves. So we have longitudinal waves and transverse waves. So like I said, if I took, and I'm going to show you tomorrow an example, but a wave is just going to be like this. So this is similar to an ocean wave. So the waves on top of an ocean go like this, and this is what we're going to see. Now it's hard for us to see the pendulum and the spring as a wave that looks like this, and I'm going to show you an example tomorrow in class how that actually ends up looking the same way. So from your pre-calculus, we know that this function y equals a sine x, and we're going to be working on how these are. Okay, so the two types of waves that we're going to be talking about, they're both mechanical waves. One is a transverse wave and the other is a longitudinal wave. So a transverse wave comes from the word trans, which means across. So we're going to have a wave that's going to be traveling across. It's a wave whose properties, or the particles of the wave, move perpendicular to the direction of the wave. So here's an example of a transverse wave. The wave motion is going up and down. The particle motions are going up and down. So if I talked about one spot right here on this rope, and if I were to wave it like this and it was going to be going up and down, this particle stays exactly where it is. It's moving, but it's going up and down. But the wave itself, you're going to see moving that way. So this is perpendicular to the wave motion. So a wave whose particles move perpendicular to the direction of the wave. This is our transverse wave. Okay, then we're going to talk about a longitudinal wave, and this is a little bit more difficult for some people to understand, but it's going to be a wave whose particles move parallel to the direction of the wave. So the particles are going to be moving this way, and the wave is going to be moving this way. And I'll show you a better example tomorrow, but if I took a slinky like this, and I were to shoot, you can see that the wave is going that way. Okay, it's kind of hard to show it on the video, but you can see that this area of thickness of the spring is moving this way. So the particle and the wave are both moving in the same direction, where the other one is going like this, up and down. Okay, so we're going to be talking about those two types of waves. Okay, so some definitions that we're going to be talking about, and most of you guys are probably familiar with these definitions just from pre-calculus. But if a wave is looking like this, we're going to be talking about first the amplitude. The amplitude is going to be the distance from its equilibrium position to its highest point. It's also the same as the equilibrium to the lowest point. What it is not is the distance from the top to the bottom. So the amplitude, and we're going to call it A, is the maximum displacement of the wave, only dependent on how the wave is generated. So right here is an example of two A's. The amplitude here is from here to here, or from here to here, and this amplitude here is much larger. than it is from here to here. And it's just how I generate the wave. So if I go big, it's going to be a bigger amplitude. If I go small like this, it's going to be a smaller amplitude. Okay? Another one definition is a wavelength. And we call this lambda, and it's a Greek letter. It kind of looks like that, and then that. Okay, so lambda is the wavelength. It's really the length of the wave. Okay, so what we do to measure our lambda is we take it's the distance between two adjacent similar places on the wave. So if I choose this point and that point, it's going to be the distance from there. I could also choose the bottom point and another bottom point. I could also choose an equilibrium point going up and another equilibrium point going up. So that wavelength will be the same either way. Okay, so here's an example. If I wanted to choose this point and this point, or this point and this point, okay, and I can choose this point and this point, okay. A lot of times it's easier to look for the two troughs from here to here, and then you can see that this is going to be our lambda. Okay, the speed of the wave is pretty much how fast is that wave traveling. So the speed, once again, is velocity, how fast the wave moves. Velocity is your displacement over your time. In wave motion, the displacement is the lambda, and the time is the period. So it's lambda over time. And in most cases, in general waves, the wavelength is always equal to 2 pi. And you guys would have learned that in pre-calculus, so we could really say that the velocity is 2 pi over t, the period. Okay, so let's try some examples. Okay, a piano string is tuned to middle C, and it vibrates with a frequency of 262 hertz. So here's our frequency, 262 hertz. Assuming the speed of sound in air is 343 meters per second, find the wavelength, this is our unknown lambda, of the sound wave produced by the string. Well, we know that the velocity is equal to the lambda over the period, and we're looking for lambda. Well, we don't know t, but we also know that t is equal to 1 over the frequency. So our t is equal to 1 over 262 hertz. I could also say that the frequency equals 1 over lambda, so v times t, the velocity times the time, the period, is equal to lambda. And we know the velocity is 343 meters per second. And time is 1 over 262 hertz. Okay, and I think I did something. Oh, no, I did that right, sorry. Okay, and so our lambda is going to be equal to 1.31 meters. So this is going to be our wavelength. So if we were to draw this, the distance from here to here is going to be 1.31 meters. Okay, and we'll try one more problem. Okay, I have a tuning fork. It produces a sound with a frequency of 256 hertz, okay, and a wavelength in air of 1.35 meters. What is the speed of sound in air? Okay, so we're going to start with our velocity is our lambda over our time, and we're looking for velocity, 1.35 meters, and our time is 1 over 256 hertz. So I have 1.35 times 256 hertz, which ends up being 346 meters per second. So from these examples, you can see that the velocity of these sine waves are very fast. Okay, so that's all we're going to be doing today. So don't forget to do your assignment for tonight, and we will see you tomorrow in class.